Hey, do you know how our Earth came in existence, how our solar system, and even how our galaxy came into existence? Today we will talk about how we came into existence. Listen, about 4.6 billion years ago, our solar system did not exist. There was no sun, no Earth, no planets. Only a giant cloud of cold gas and dust drifting through the Milky Way galaxy. Yet from this seemingly empty cloud, gravity would create the sun, the planets, and eventually life itself. This is the precise scientific story of how the solar system was born. The story begins inside a molecular cloud, a massive region of gas, mostly hydrogen, and microscopic dust particles. At some point, something disturbed this cloud. Astronomers believe a nearby supernova explosion, or shockwave from massive stars, may have triggered it. This disturbance caused part of the cloud to collapse under its own gravity. As the cloud collapsed, it began spinning faster due to conservation of angular momentum. Most of the collapsing material gathered in the center, forming a hot, dense object called the protosun. Meanwhile, the remaining gas and dust flattened into a rotating structure, known as a protoplanetary disk. This disk was the birthplace of every planet, asteroid, and comet in our solar system. The early disk was extremely hot near the center. At temperatures above 1,500 Kelvin, the first minerals began condensing out of the gas. These earliest solids are called calcium aluminum-rich inclusions, or CaIs. Scientists discovered Ca is inside primitive meteorites and used radioisotope dating methods to determine their age. The result, CaIs formed 4.567 billion years ago, which marks the official starting time of the solar system. After Ca is formed, the disk continued evolving. Within 1 to 3 million years, molten droplets of silicate rock called chondrules appeared. These droplets likely formed through intense heating events such as shock waves in the disk. As dust grains, CaIs, and chondrules collided, they began sticking together. Through continuous collisions and gravitational clumping, they eventually formed planetesimals, solid bodies typically tens to hundreds of kilometers across. Planetesimals are the fundamental building blocks of planets. Many of these bodies heated internally due to radioactive elements like aluminum-26, which caused them to differentiate, forming metal cores and rocky mantles. Meteorite chemistry reveals that the early solar system quickly separated into two distinct reservoirs. First, inner disk, non-carbonaceous region, where rocky bodies like Earth, Mars, and Vesta formed. Second, outer disk, carbonaceous region, where water-rich asteroids and giant planet materials originated. This separation likely occurred because Jupiter formed very early within the first few million years. Once Jupiter grew large enough, its gravity acted as a barrier, limiting the exchange of material between the inner and outer solar system. Evidence from meteorites also tells us that the Sun probably formed in a dense star cluster, similar to regions like the Orion Nebula. In these environments, massive stars emit strong ultraviolet radiation and often explode as supernovae. Meteorites contain short-lived radioactive isotopes such as aluminum-26 and iron-60. Because these isotopes decay quickly, they must have been produced by a nearby supernova shortly before or during the formation of the solar system. Scientists estimate this explosion occurred roughly 0.1 to 1 parsec away, cosmically close. These radioactive elements heated early planetesimals and accelerated their geological evolution. Planet formation occurred through a process called accretion. Small particles collided and stuck together, gradually forming larger bodies. Modern theories such as streaming instability explain how dust particles concentrated into dense clumps that collapsed into planetesimals roughly 10 to 100 kilometers in size. From there, planets grew by two main processes. Planetesimal accretion, collisions between large, solid bodies. Pebble accretion, rapid growth by capturing small, drifting particles. The giant planets, Jupiter, Saturn, Uranus, and Neptune, likely formed through core accretion. In this model, a solid core of about 10 Earth masses forms beyond the snowline, where water and other volatiles can freeze into ice. Once the core becomes massive enough, it begins pulling in large amounts of gas from the surrounding disk. This runaway gas capture produces a gas giant. Jupiter probably formed within a few million years, before the gas disk dissipated. After the gas disk dispersed, the inner solar system was filled with leftover planetesimals and protoplanets. Over tens of millions of years, these bodies collided and merged through giant impacts. This chaotic stage eventually produced the rocky planets: Mercury, Venus, Earth, and Mars. One of these massive collisions likely formed Earth's moon. Meteorites act as fossils of the early solar system. Their isotopic compositions provide a detailed timeline of early events. Even more evidence comes from asteroid sample return missions. NASA's OSIRIS-REx mission collected material from asteroid Bennu, discovering amino acids and nucleobases, which are essential components of DNA and RNA. Japan's Hayabusa 2 mission returned samples from asteroid Ryugu, revealing thousands of organic compounds. These findings suggest that water and organic chemistry were widespread in the early solar system, and such materials may have helped seed life on Earth. Astronomers now observe planet formation directly. The ALMA radio telescope captured images of the young star HL Tau, showing rings and gaps inside its disk, likely created by newly forming planets. The James Webb Space Telescope has also detected water ice, carbon dioxide ice, and organic molecules in protoplanetary disks. These observations confirm that planet formation is a natural and common process in the universe. Today, scientists understand that the solar system formed through a sequence of events. A molecular cloud collapsed, forming the sun and a rotating disk. Dust condensed into the first solids. Solids formed planetesimals. Planetesimals grew into planets. Over millions of years, this process produced the complex planetary system we live in today. From a cloud of cosmic dust to a star surrounded by worlds, and on one of those worlds, Earth, where life eventually emerged. If you like this information, don't forget to subscribe. We will meet again in next video.